Hello, ladies and gentlemen. The paper we present today is called Silicon Photonic Microring Resonators Design Optimization under Fabrication Non-Uniformity. To give an overview of what we are going to present, I'll be giving you an introduction of microring resonators, speak about all the parameters involved in silicon photonic microring resonators, talk about design space exploration, and give an optimization of this design, and also speak about our results. Microring resonators are one of silicon photonic devices, and this is how they look like. They have an input port, a through port, a drop port, and an add port. Microring resonators have advantages such as the footprint is compact and also functionality such as can be used for filtering, for modulation, as well as switching. All these advantages are overweighed by the disadvantages. The disadvantages is that it's highly sensitive to fabrication process variations. A microring resonator is said to be in resonance when an optical wavelength on its input port matches with the resonant wavelength in the microring, and one can see a signal at the drop port. And when the microring is not in resonance, one can see a signal at the through port. And the peaks of the output seen at the through and the drop port can be considered as resonant wavelength. And this is how a microring resonator works without any fabrication process variations. To speak about fabrication process variations, these fabrication process variations cause change in the waveguide width and thicknesses. For example, the waveguide can expand or can be thicker and also can be less, whereas the thickness can also increase and decrease with respect to fabrication process variation. This variations can occur both at the input port and the ring at the input waveguide and the ring waveguide, and these width and thickness variations cause change in resonant wavelength. As one can see that the resonant wavelength shift has occurred because of these fabrication process variations. In order to compensate these fabrication process variations, high energy particles are used. Also, thermal tuning is used to change the dimensions of the input and the ring waveguide width so that these variations are compensated. To speak more about what microring resonators are, and we look into three main parameters to improve our design space exploration. And the three main parameters we look into is the resonant wavelength and its shift. We look into crossover coupling as well as Q factor or quality factor. On the right hand side, you can see that all these parameters are used which make an impact on the microring resonator, such as the input waveguide width, which is WW, the ring waveguide width, WR, the gap, the straight through coupling, crossover coupling, and the radius. To speak about resonant wavelength shift, resonant wavelength shift is a function of the highlighted factors, which is the input waveguide width, the ring waveguide width, and the radius. Changes in any of these causes change in uh, resonant wavelength and causes resonant change in resonant wavelength shift. For example, changing the radius causes change in initial resonant wavelength, and that can impact the change in resonant wavelength shift. Similarly, crossover coupling can be defined as the amount of power one can see at the output uh, port, and it depends on the highlighted factors as shown. To give an overview of how coupling impacts, if this is how normal coupling looks like, a reduced coupling would mean this. And to give a comparison, there is increase and decrease in coupling with changes in gap. Having more coupling would mean that a signal is better detected at the output, and ideally a designer would want as much coupling as possible, and reduction in coupling is not recommended. To speak about quality factor is the third parameter that we used for design space exploration, and it can be defined as a measure of sharpness of resonance relative to its central frequency and Q factors. And it depends on almost all the factors in microring resonator. A higher bandwidth signal can lead to lower quality factor, which is not desirable since it can lead to error in detection of the signal, and very high Q factor can lead to tuning of signal at a very particular frequency so that the output can't be detected. Hence, it's critical to have a desirable Q factor which can make readings the signal at the output easier. This is how we propose the design space exploration. On the left hand side is the resonant wavelength shift with respect to width, which is the blue line, and thickness, which is the green line, when the input and the ring waveguide width are equal. In this situation, we can see that the resonant wavelength shift with respect to width decreases constantly as the waveguide width increases, which corresponds to a fact that the tolerance increases, that the amount of resonant wavelength shift one sees at a waveguide width, at a thicker waveguide width, is much lesser, or the tolerance is much higher compared to a waveguide width which is at the range of 300 to 500 nanometers. Um, this is a good functionality one would like to use. However, when we look at the crossover coupling, which is on the y-axis on the right-hand side in pink, we can see that the crossover coupling reduces constantly as we keep on increasing our waveguide width, which corresponds to a fact that the output cannot be captured completely. Hence, we would want to not have that in our design. However, we would still want to have increased tolerance in our design. And we propose this model where the ring waveguide width, which is WR, is not equal to the input waveguide width, which is WW. And we can see that we can for the fact see that the similar trend occurs with respect to resonant wavelength shift with respect to width and thicknesses, that it constantly decreases corresponding to increase in tolerance. However, we also see that there is an increase in crossover coupling when we have our waveguide width, input waveguide width, or the ring waveguide width twice as the size of input waveguide width, which opens up a lot more possibilities for signal detection at the output when we have ring waveguide width thicker than the input waveguide width. And we use this functionality to propose an optimal design space exploration. Um, when we speak about crossover coupling and Q factor, of tolerance occurred in those micro rings that we propose at those design points, we can see that there is still chance of improvement of with respect to tolerance at all the proposed design points. On the right hand side is the total resonant wavelength shift graph, which has inclusion of width, uh, resonant wavelength shift with respect to width and thickness both, and also different scenarios where width variations are greater than thickness variations, or thickness variations are greater than width variations, and both are equal. In this situation, if a designer has an example such as a designer wants maximum coupling, a design point A would be optimal for high coupling, and a designer in the case where the width variations are greater than thickness variations, a designer can end up choosing design point A, and it would be the design of the microring would be much more tolerant than when both width and thickness variations are equal. Hence, this can give a lot more possibilities to choose between what sort of ring a designer is going for based on the width and thickness variations occurred on the die or the wafer. When we fabricate our rings, these are the fabrication results which we see. We have three different rings. The first one is microring 1, which has input and ring waveguide width of 400 nanometers each. The radius is 10 microns. The gap between the input and the ring waveguide width is 100 nanometers. And we can see that the second micro ring resonator is a racetrack resonator, which is shaped in form of a racetrack, has input and ring waveguide width of 800 nanometers. The radius is 6 microns, and gap between input and ring waveguide width is 100 nanometers. And the third one is the proposed design, where the input waveguide width is set to 400 nanometers, the ring waveguide width is set to 800 nanometers, which is about twice. The radius is set to 100 microns, and the gap between input and the ring waveguide is set to 100 nanometers. Um, the chip size was used. The chip size used was about 1.5 times zero point 0.6 millimeter square. Uh, Electron beam lithography process was used to fabricate these rings. Tapers were used to ensure single mode operation in all these rings, and waveguide width thickness was set to 200 nanometers. 10 identical copies of each microring resonator was fabricated to check redundancies. Uh, and all this was tested using automated testing facility with no thermal variation. When we look at the results for microring resonator 1, we see that there is high coupling, acceptable Q factor, and low tolerance. The resonant wavelength, which the desired resonant wavelength is very much farther from what we actually see, hence the tolerance is low. Similarly, when we look at a microring resonator with 800 nanometers input and ring waveguide width, we see that the coupling is, however, low with high Q factor and high tolerance. And a good trade-off is given between these both parameters, where we can see good coupling in microring resonator 3, acceptable Q factor, which is much better than microring 1, and we see good tolerance as we see in microring resonator 2. To speak more about resonant wavelength shift, we can see that in microring resonator 1, the average resonant wavelength shift is seen about 7.1 nanometers, and in microring resonator 2, the average resonant wavelength shift is seen about 1.8 nanometers, which says it's highly tolerant to any variations which occur. Um, in the proposed model, where the input waveguide width is set to 400 and the ring waveguide width is set to 800 nanometers, we can see that the average resonant wavelength shift is about 2.1 nanometers. It's not as good as seen in microring resonator 2, but it's not as worse as seen in microring resonator 1. So this gives us an amazing opportunity, and it proves our point, which says having your width waveguide about ring waveguide with about twice the input waveguide width would give you better tolerance, better coupling, and acceptable Q factor to be able to read signals at the output port. In conclusion, I would like to say that we've developed effective solutions to find optimal parameters in microring resonators to improve tolerance, crossover coupling, and Q factor. In applying these concepts in electronic design automation, one can integrate these proposed models into an automation tool and use it further. Thank you.